Hey guys, what's going on? This is Jeff again. So today I want to talk to you guys a little bit about this idea of dimensional analysis. So there's kind of a few different ways to do this. This video, it's not really going to be where I kind of just teach you guys how to like multiply by 1 in different ways. So, if you have something like, I don't know, like 2 grams for every like 10 milliliters, and if you wanted to convert that to like kilograms per liters or something, yeah, I don't quite want to teach you exactly like how to do this conversion. You can find that maybe like in your chemistry book or something like that. I'm sure that there are lots of other videos. I more want this to be kind of like I want you guys to get kind of a conceptual understanding of what dimensional analysis really is about. And yeah, so it's just kind of like more of a conceptual thing. So it's a little bit more qualitative and again, and not so quantitative. Let me start out kind of with this idea of dimensions. Now with this, I'm not so much talking about, like the first dimension, the second dimension, or the third dimension. I'm more just kind of talking about the main sort of units for physical quantities. So let's just say like we have, just like some block. Here, we'll just call it block. It's a block by the way it is. So it's just sitting there. So there are different sort of physical quantities that this block would have. So the first, I'll just say that it has mass. So this is probably, I don't want to say that it's the most fundamental of the dimensions, because I don't know if you could say that one dimension is really more fundamental than the other. In fact, yeah, I definitely don't think that you could say that. But one way that we can, but one physical property that we could say that this block has, we'll say that it has mass. So that's kind of one of the main base units when we're kind of talking about this whole dimensional analysis thing. The other one is that, well, if I wanted to measure this block, okay, I put some like meter stick here. Whoop. Well, we would say that it has some length, right? So that's kind of another one of the main dimensional qualities of matter. So we'll say it has length. The next one is a little bit more conceptual, applying it to the block example. But let's say, I stick this meter stick on, at some time. Let's say I do it, I don't know, like 12:04 p.m. I mean, yeah, like the block itself doesn't really have time. Time is just, it's just another kind of fundamental quantity that we use to measure sort of different things. So, I mean, if we had, like if this block was moving, if we say it had some velocity, some meters per second, then definitely like that would be a unit of time. And I'll kind of give you guys examples of this. But I would definitely say time is another one of the big dimensional qualities. These are probably the 3 that your book is going to really stick to. It's kind of like what most of our fundamental units kind of just go back to, is a unit of mass, is a unit of length, or is a unit of time. I just want to add in one more dimension though, and that would actually just be the unit of charge. So for those of you who have taken Gen Phys 2, then you have definitely talked about charge before. But for example, I mean, this block, every proton and every electron in this block is going to have some unit of charge. So charge is a property of matter that is as fundamental as a unit of mass. So just every piece of matter, it has both mass and it has both charge as well. It can either have a negative charge or a positive charge. If you're talking about something like a neutron, I think technically a neutron is a proton plus an electron, but they're like morphed together. I honestly quite haven't studied the neutron at a high level, so I'm not quite sure. But definitely, like if you have a piece of matter, then it's definitely going to have mass, and it's also going to have charge. Okay, cool. So let's just kind of do a simple kind of conceptual example, and kind of get to the meat of kind of like a tool or a skill that you guys can kind of have, or that you guys can kind of use. So let's say, I don't know, I have some quantity here. Let's just say I have like meters per second, and I want to know if that's dimensionally equivalent to, I don't know, let's say to kilometers per hour. So what I could do is, you know, I could convert meters to kilometers, I can convert meters to hours and see if everything lines up. But in order to kind of say whether or not these are dimensionally equivalent, you have to kind of go back to these more fundamental things. So meters, so that's just going to be a unit of length. So I'll just write an L there. Seconds, that's going to be a unit of time. So okay, so I have length divided by time. All right, that's fine. For kilometers, well, that's also a unit of length. Okay, and then hours, that's also a unit of time. Okay, nice. So these, in fact, would be dimensionally equivalent because it's just length divided by time equals length divided by time. So we would say that those are dimensionally equivalent. Nice, great. You did your first dimensional analysis problem. Can you guys see that? There we go. Sorry. Cool. So those are dimensionally equivalent. All right. Well, let's maybe do kind of a little bit of a harder example. Let's see here. What if I said we have like kilograms, meters per second squared, and we want to know if that's dimensionally equivalent to something like, I don't know, let's say grams, inches per microsecond squared. Okay, so kind of the same process here. So kilograms, that's going to be a unit of mass, so m meters, so that's just a unit of length, and then seconds, so that's a unit of time, but it's squared, so it's a unit of time squared. All right, cool. So let's see what's going on with this one. Well, grams, that's also a unit of mass. Inches, that's also a unit of mass. Sorry, a unit of length, not mass. And then microseconds. So the micro, that's just 10 to the negative sixth. So micro equals 10 to the negative sixth. So that's just a factor. It's not like an actual dimensional unit. Seconds, well, that's just seconds because that's what it is. So it's a unit of time. So this is also a unit of time squared. Okay, cool. So I have mass length over time squared. Here we can even write that all out. Mass times length times t squared equals mass times length over time squared. Okay, sweet. So those are dimensionally equivalent. So this is just kind of like a really good way, you know, if you're getting certain answers, and if you don't know if you really sort of have like the right units, you can always go back to the base units, you know, units of mass, length, or time, and see if kind of like your starting answer is dimensionally equivalent, or well, not your starting answer, kind of like your starting problem is dimensionally equivalent to your final answer. So it kind of seems like maybe it's not that important of a skill, but as units kind of start getting more difficult, it's definitely going to be pretty important. So for example, if you had kind of a more difficult problem, so let's see here, like if I had something like, so you had, let's say Newtons per Coulomb equals volts per meter. So Newton, so that's a unit of force. Coulomb, that is going to be a unit of charge. So you can't break a unit of charge up into any of these other three units, time, mass, or length, because charge, it itself is just kind of like a fundamental property of matter. So you can't really break it up into anything smaller. But we could break up this Newton, so we'll do that. And then volts, so that's a unit of potential difference. So if you haven't taken Gen Phys 2 yet, you probably don't quite know what that is, but we can break that up into its fundamental units and kind of see if these are dimensionally equivalent. So we'll say dimensionally equivalent question mark. Okay, well, let's see here. So if I kind of put this up there. All right, so for newtons, I mean, I just kind of know it because I've used it so much. So in Newton, it's going to be kilogram meter per second squared. And then the Coulomb, we'll just say it's over C. Okay, that's fine. And then for volts, so we can write that as joules per Coulomb, and then that's going to be over meters. So basically what we just keep doing is, well, joules is itself made up of these more fundamental units. So we want to kind of, we want to break this up because we can't quite use, our mass, length, time thing. So we'll say we're going to break this up even further. So with joule, it's going to be kilogram meters squared per second squared. And then this is all going to be over Coulomb. And then that is all going to be over meters. Man, right? This is so fun. So honestly, I mean, a way that you could do it is you could just leave it as like kilogram, meters, and all this kind of stuff, and just see if you eventually get to this piece. But I just kind of want to go through like the full thing and just kind of see what we get here. So if I broke this up into its dimensional quantities, well, kilogram, that's unit of mass, meters, that's unit of length, second squared, that's time squared, and then per charge. Okay, cool. So I have mass, length, per time squared, per charge. So I'll just say Coulomb, I'll leave it at C. So this is Coulomb, but they both have C, so I'll just call this charge. So mass, length, per time squared over charge. Okay, so let's just kind of do some fun algebra with this, I guess. So this is over 1. So if we flip this up, 1 is on top, and then meters is right here. All right, that's great. So I guess we can multiply this whole thing through kilogram meters squared per second squared per Coulomb meter. That's going to be over 1. I'll just bring this down here, and we'll do just a little bit more just to make it kind of its fully simplified form. Kilogram meter squared per second squared times Coulomb meter, because we just flip this guy up. We do the little dot floppy thingy. And then, so this is going to simplify to kilogram. So the meters cancels with that. So kilogram meters per second squared times Coulomb. Ah, okay. Here's something. Oop, can you guys see that? There we go. So this, here's something interesting. If we broke this up, so this is mass, length, time squared, and then charge. Mass, length, time squared, and then charge. Well, does that match this? Well, it does, because we can flip this charge up 1 more. So this is multiplied by 1 over C. That goes away. So we have mass times length times time squared times charge. And that is dimensionally equivalent to mass times length times t squared times charge. I think I forgot the little c there. So yeah, this is just, so these units here, this is actually the unit for the electric field. So you can write the unit of the electric field either as newtons per coulomb or as volts per meter. And we know that we can do that because we just showed that those units, these guys right here, it's dimensionally equivalent to this guy. It's just mass times length over time squared times charge, which is dimensionally equivalent because we just did all this algebra stuff, which is equivalent to mass times length over time squared times charge. So, if you're ever confused about whether units are dimensionally equivalent, break them down into kind of these four main basic units, and then see if you end up getting the same units on the left side. If you get the same units on the left side as well as on the right side. So again, I mean, it's a pretty cool thing. Definitely, as you get into kind of higher level physics, you can kind of really start thinking about kind of like how dimensions sort of like start morphing. And I mean, obviously, we have the famous equation E equals mc squared. So like units of energy, how that could somehow be a unit of mass times a velocity squared. So it just kind of gets into some really interesting stuff. So yeah, I hope that helped you guys with dimensional analysis, and I'll see you guys in the next video. Thanks.